Hey guys, today we're going to be solving LeetCode question 837, new 21 game. This is a medium LeetCode problem, but it's actually a little tougher than a usual LeetCode medium problem. I would say it's leaning towards a hard problem. What makes this problem difficult is not just the solution, but the question, like the problem statement itself. Because there are like three variables and they've thrown in some probability in there. It's difficult to grasp the essence of the problem in one reading, honestly. But yeah, we'll get there. I'll explain everything. What I'm going so this is the solution is based on dynamic programming. I'm going to present two solutions. The first solution is actually a TLE solution in that it will exceed the time limit on LeetCode, but it's easier to understand and it will lay a good foundation for us to proceed to the more optimal solution, which is also a dynamic programming solution, but we'll also integrate a sliding window component in there. So don't think about the sliding window or dynamic programming right now. We'll get there, but I was just setting the expectations right. Anyway, let's get to the question. Cool. So I hope you've read the question. So the as I mentioned, the problem with this question is that there are like three different variables that we need to consider when we think about the solution. So what we'll do first is we'll just eliminate some of those variables. Okay, we'll not think about everything at once. What they have said is given a range from 1 to max points. Yeah, let's say max points is 6, so our range becomes 1 to 6. Cool. What they're saying is we can draw numbers from this range and all numbers can be drawn with equal probability. So say the probability of drawing a 2 is equal to the probability of drawing a 5, and we'll keep drawing numbers from this range. So say we draw 2 and then we draw 4, we get to 6. Say we draw 6 after that, we get to 12. We'll keep summing this up. And when do we stop, right? That stopping, that threshold is defined by this k, right? So say k is 18. What they're saying is as soon as we touch 18 or we cross 18, we stop the game, right? Basically, there is no way to end the game until your sum is less than 18. As soon as it touches 18 or crosses 18, we stop the game, right? And if you're familiar with this card game 21, that's exactly what happens, right? If you reach 21 or if you cross 21, you stop drawing. I am not familiar with that game, honestly, but I think it's that's exactly the idea of that game. Anyway, I digress. But so yeah, this k is the threshold, right, of when we stop drawing. And so basically the game can never end until you have drawn k or more than k points, right? What they want for the solution is the probability. Okay, forget probability. What is Okay, no, let's think about probability. What is the probability that Alice has n of fewer points? Okay, and n will always be greater than k, greater than equal to k, which is kind of important for this question. Okay, say n is 21. Yeah, so what is the probability of us getting n or fewer points? Now, when does that fewer points end? We know the upper limit n. When do those fewer numbers end? It ends at k, right? Because the game cannot end until you cross k. So when they say they want the probability of Alice reaching n or fewer points, what they mean is probability of n would be probability of n. Sorry, not. I'm sorry. The solution would be the probability of n plus probability of n minus 1 until probability of k, right? That is the lower limit because the game couldn't have stopped unless we had crossed k points. And so the least we could have, the least sum that we could have reached when the game stopped is k. So when they say n or fewer points, what they mean is this range. The probability that our final sum is in this range, k to n, and k will always be less than or equal to n. They've ensured that. Cool. This is the problem. This is uh, yeah, this is the problem statement. I hope that was clear. Let's get to the solution. Okay, I'll dive right into it. Let's define our recurrence relation first. What would be dp of I? Okay, let's define this as the probability of reaching the number I. Cool. Let's just define that. Now let's say let's just take this example. Okay, we'll keep n21, k 18, which is the threshold, and max point 6. Okay, basically we can draw from 1 to 6, any number from 1 to 6 with equal probability. There is no bias there. Cool. So let's say we want to know the probability of reaching 21, right? Now what are ways of reaching 21? Actually, let's start with something simpler. Yeah, in general, yeah, let's start with something simpler. What is the probability of reaching 14, say? Okay, that so I'm not this is let's yeah let me not confuse you with putting in too many elements here. Just think of this objectively. What is the probability of reaching 14 anywhere, like anywhere, anytime during the game? What is the probability of reaching 14? So the probability of what are ways to reach 14? Basically we could have reached 13 and then drawn 1 to reach 14, or we could have reached 12 and drawn a 2 after that from that range to reach 14, right? So what I mean is the probability of reaching 14 is the probability that we have reached 13 somehow by drawing our numbers, and then into the probability that we drew a 1 after that. Yeah, please note that this dp is the probability of reaching that number, and this probability is the probability of picking that number. There's a difference there. Okay, it's very important to understand that difference. Anyway, so we could have also reached 14 from 12 and picked a 2 from that. Okay, this should not be a dot. Okay, and I hope you're familiar with like basic probability laws, because we want these two events to occur together, like reaching 12 and drawing a 2, so we multiply that. But there are like because we could reach 14 via this route or this route or these are the other routes, so we sum it up. Like if you know basic probability, this should be easy to understand. Then so we'll keep doing this, right? What is the largest number we can draw from this range? 6, right? So probability, so dp of something into probability of 6, right? So this should be 14 minus 6, okay, which is 8, right? This is the base of our recurrence relation. And if you noticed, what I did was this was 14 minus 6, right? Because that is the maximum distance behind from where I could have reached 14. Yeah, and if you think about it, this 14 is max points, right? Forget this 8, and this 6 is also max points. So as you see, I'm getting to the recurrence relation slowly. Okay, Now let's define this in terms of our variables. So dp of I, okay, this I can be any number, um, would be dp of I minus 1 into probability of drawing a 1 plus dp of I minus 2 into probability of drawing a 2 until dp of I minus max points into probability of drawing max points. Now, as I've mentioned a couple of times, and as it's mentioned in the question, each draw is independent and the outcomes are equal probabilities. What that basically means is the probability of one, probability of two, probability of max points. They're all equal, and they're all equal to 1 upon max points. Okay. If again, um, probability is defined by the favorable event upon total events. So the total events is max points, because you can draw max points number of points, and one is the possibility of drawing that one number of interest, like of probability of drawing two is one out of those max points numbers. Like I hope I hope this is clear. Like if you know basic probability, this should be clear. So what that basically means is this is 1 upon max points right. Yeah, and this is basically a recurrence relation. Let's simplify this more, because it adds value. It will help us think better as we go. I'm just doing some basic algebra here. I'm getting the fraction outside and writing this as a sum of dp of I minus 1 until dp of I minus max points, and that's it, honestly. Now there are a few corner cases I have left out. um, I I guess I could. Okay, let me just mention one important edge case, and the rest we can cover as we code, right? Because it will be easier that way. Because one corner case that I do want to mention at this point is, say, so this is all fine as long as this 14 is less than the threshold, right? But there are two edge cases to consider here. Say, what is the probability of reaching 3 and your max points is 6? So in that case, your recurrence relation will at some point want I minus max points, which will be 3 minus max points, 3 minus 6. So you will be at dp of 3 minus 6 minus 3, which makes no sense. So this is one edge case where we have to consider the fact that our like we don't have numbers behind 0. That is the first edge case that we need to think of. This is basic, like this is something that you would have thought of anyway. The other important edge case is at the other end, um, is at the other end of the problem. Okay, what think of this? What would be dp of 21? Now, important things to consider here. You cannot reach dp of 21 from dp of 20, right? 21 minus, so if I is 21, I minus 1 would be 20. Okay, there is no way of reaching 21 from 20. Why? Because if we have reached 20 already, we will not draw. We are above the threshold. So if we have reached 20, we can never get to 21, right? This is an important edge case to remember. Similarly, if I have reached dp of 19 or dp of 18, okay, it is not possible for me to reach DP of 21. Okay, so when we calculate the DP of 21, we will not include DP of 20, 19 or 18 in our solution. This is important to remember. This is a very important edge case to remember. We'll only consider DP of 17 and lesser until we reach DP of I minus max points, which is 21 minus 6, which is 15. Right? There's actually only one here. I don't know why I put 3 dots. Anyway, DP of 16. Okay, we will not consider these three elements. This is the other edge case to consider. Okay, if you understood everything until this point, the next two solutions that I present will be easy to follow. Okay, um, let's dive right into it, because this is already going to be a long video, and I want to proceed fast. Cool. We'll handle an edge case first. If k is equal to 0, return 1.0. What this edge case what this check means is, if the threshold is 0, which means we cannot start the game at all, right? Like, before our game starts, our score is already 0, and if the threshold is 0, we've already crossed it, or we are already at the threshold, so we don't need to start the game. So our score will never increase beyond 0, and whatever the value of n be, maybe will always remain at a score less than or equal less than n, right? So the probability of Alice having n of fewer points is 100%, which is indicated by probability 1, which is what this edge case handles. Moving on. So basically, with this solution, I'm going to construct this relation like entirely, right? I'm going to put in two for loops, and that's why it's going to TLE as well, right? But I'm just doing this because it's easier to understand it, and it will be easier for us to move to the more optimal solution from this point. Okay. So the idea is we're going to calculate DP values for all possible scores that we can get from this game, and then we'll just sum up the DP values that we need for our solution. Okay, so we know that the lowest score we can get from this is 0 if you don't start, but let's not think about that. The lowest is 1, let's say. And what's the max score that you can get from this game, right? Now you know you have to stop the game when you get to K. So, but think about it. The largest score that you can get is if you are at K minus 1, like 1 less than K. Just like you haven't reached the threshold, you've reached the maximum points that you can before reaching the threshold. And if at that point you draw the maximum possible points, right, which is max points or 6, that will be your maximum score. And as soon as you reach that maximum score, you would have crossed the threshold, so you cannot draw anymore, right? So the max score that you can reach in this game would be K minus 1, that is 1 less than K, the threshold, plus max points, because that's the max points. That's the maximum jump you can make from that point, right? So that's what we are going to do. We're going to calculate DP values from 1 to max score, and then for the final answer, we're going to just sum up the DP values from K to N, right? As I mentioned, N is the high limit that they have given us, and the lower limit is something that we have found. Like, the game can never end at a score that is less than K. It will always end at K or greater than K, and it will move on to N. And N will always be greater than equal to K. So that there will be no index, what should I say, mismatch, not mismatch, but you get the idea. There will be no issues there. So this is a one-dimensional dynamic programming solution. This is me defining a 1D array, 1D double array, initializing all values to 0. The size will be max score plus 1, right? Because we want DP of max score as well. That's why I'm going to initialize it to max score plus 1, and I'll just I'm going to set the size as max score plus 1, and I'll just initialize dp of 0. What would be dp of 0? What is the probability of reaching number 0? 1, right? Because if you don't start the game at all, you're already at 0. So the probability of reaching 0 is maximum is 100%. So I'm going to initialize that as 1.0. Now I'm just going to insert my two for loops, right? So we are going to calculate dp of I values for all possible scores that we can get from this game. So that is I to max score. Okay, and then we're going to put in an inner loop. This inner loop is going to help me construct this recurrence relation for every dp of I. The j will basically be these values, 1, 2, max points, whatever we are subtracting from I. Cool. So this will go from j to max points. Yeah. Now we're going to handle those two edge cases that we spoke about, right? What we want is I minus j, right? So let's put in some checks for I minus j. If I minus j is greater than equal to 0, right? As I told you, like, what if your I is 3 and your max points is 6, and you do an I minus j, you get 3 minus 6 minus 3, dp of minus 3, which makes no sense. So we have to ensure that the least value we pick up from our past calculated dp values is dp of 0. That's why I'm putting in greater than equal to 0, right? And now we have handled the problem at the lower end of the problem. Now we'll handle it at the other end. I'm talking about that edge case, this edge case, dp of 21 that I told you about, where in calculating dp of 21, we will not consider dp of 20, 19 or 18, because if you have reached any of those numbers, you can never reach 21, right? You will never draw again because you've already crossed the threshold at dp 18, 19, 20. So this next condition will handle that. So this has to be less than k. Cool. Like keeping this example in mind, if you do some basic mathematics, you'll arrive at this condition. This should be easy to do. Cool. Moving on. Let me just put this in parentheses. Okay. So dp of I will be dp of I minus j divided by, and this is me just casting max points, right? This, I'm dividing by this to account for this fraction. Cool. And that's it. Like at this point we would have calculated dp values for all possible scores. Okay, so now we'll construct the solution, which is we'll sum up dp values from k to n, which should be very straightforward, right? Let's initialize the result as 0 for I in k to n. The result will be just the summation of these dp values, and that should be it. That's it. I'm going to run this code, and this will running the basic test case will pass, but when I submit it, it will expectedly exceed time limit, which makes sense, right? Like so many for loops. Yeah, so you see it exceeded the time limit. Now we can move on to the more optimal solution. Okay. Now, let me lay the foundation for the more optimal solution. Now, let's look at dp of 14, right? What is, let's call this, okay, this is a constant, right? Let's just call this c. So this will be c into dp of 13 plus dp of 12 plus, and we'll go on until dp of 14 minus 6 8, so dp of 9 plus dp of 8. Yeah, this is how it will be. What about dp of 15? Again, c into dp of 14 plus dp of 13 plus like this, plus dp of 15 minus 6 9, so dp of 10 plus dp of 9. Cool. So if you notice, the only difference between dp of 14 and 15 is that we have added one term to the starting, to the front of this sum, and we have removed one term from the tail of this term, right? The rest of the terms remain the same. So the idea is, if we maintain a running sum, okay, a running sum of running sum, what I mean is, if we maintain a sum of these values and just manipulate those front and end terms and just keep reusing that, it will be much more faster, right, than doing this entire for loop. That's the basic idea. I'm going to call this one sum the running sum. Okay, and this is basically the numerator. By that I mean is, because c is 1 upon max points will go to the denominator. We are just going to keep manipulating the numerator, and this running sum will be the sum of all dp values that can actually reach I. Yeah, that idea remains same, just that like maintain, this is the sliding window part. We are like sliding over all the numbers that can reach the subsequent i's, and just manipulating a little, manipulating at the front, manipulating at the back, and calculating the dp values. So that's the idea. And again, we will have to handle those two edge cases that I mentioned earlier. The one which is like the edge case at the zero end and the edge case at the top end, right? Let me just call this edge case 2, because I think edge case 1 is easy to remember. Edge case 2, edge case 1 is the zero case. So these two edge cases we'll handle. Okay, I think this is enough for me to move on to the next solution. Like, I can start coding and I'll explain as I go along that. Okay, and that's a very elegant solution. Like, if you've understood everything until this part, you'll actually enjoy writing that, because it is very fast, and yeah, it's just an elegant solution. Cool, let me just keep this around. I'll comment this. I'll also remove this so that we can start fresh. Cool. So adding some edge cases first. If k is equal to 0, actually I shouldn't have deleted everything, right? I'm just going to repeat. Okay, I've already explained this edge case. I'm going to define the dp array. This time I'm just going to define the dp array until n, right? Because that's, we need only until dp of n. I won't do it to max code like the previous solution. So initializing everything to 0, the size to n plus 1, because we would need dp of n and dp of n minus 1 until dp of k, and we'll just initialize dp of 0, right? dp of 0, as I explained earlier, will be 1.0, 100% probability. Now I'm going to introduce the running sum. Okay, the running sum will be this numerator value. Okay, so I'm just going to call this running sum. It will be a double of dp of 0. Okay, I'm going to start my for loop from 1. So I'm just going to initialize. So for 1, dp of 1, the numerator will just be dp of 0, right? That's the only number that comes before it. So I'm just going to initialize running sum as dp of 0, so that I can directly use it for dp of 1, and then I'll start manipulating the dp for future dp values. Okay, cool. Let me just, this is just the numerator, the sum of dp values that can reach I. Okay, this is also the sliding window, just mentioning it. Okay, cool. Okay, let's also we're just going to I could have done this separately, but let's just do it right now. We're going to construct the result on the fly. Okay, it's easy, like you won't get confused. Let's just do it, it will be very fast. So excuse me for doing this, like I'm explicitly specifying the type and still doing 0.0, but it's fine, let's not concentrate on that. So for I in 1 to n, right, because we have already calculated dp of 0, let's start with dp of 1 and go till dp of n, because that's the maximum that we could need. Cool. So dp of I will be running sum upon double of max points, right? Okay, at this point I'm assuming that the running sum has already been prepared for the current dp of I. Like for dp of 1, my running sum is already correct because I've initialized it with dp of 0. That's what our assumption will be throughout this for loop, that at the beginning of the for loop my running sum has the sum of all the correct dp terms for the current dp of I, and for the rest of the loop, like below this, I'll actually I'll actually manipulate the running sum so that it's correct for the next dp of I. Okay, you'll understand that. Let me just add a comment. Calculating dp of I assuming running sum has already been correctly prepared. Okay, moving on, let's handle the front end first. Okay, front end of running sum. Cool, like you'll understand what I mean by front end and tail end. Basically we have to add a new term at the front of the running sum and remove one term from the tail end or the rear end of the running sum, right? And that will differ, right? This if condition, if I is less than equal to k, comes because of the dp21 case that I told you about, right? We are going to handle that right here, because you remember, as soon as we touch k or we go beyond k, we can't include those dp terms in for dp values that we calculate after k, right? Because dp of 21 is after dp of 18, where 18 is the threshold, so we can't include dp of 20, dp of 19 or 18. So as soon as we touch k or we cross k, we stop including those values, and that's the logic that will go here. If I is less than k, we are below the threshold, we can add terms peacefully. No, there's no problem. Okay, so that's what we'll do. We'll add the current dp value to the running sum. Why are we adding the current dp value? Because we are actually preparing the running sum for the next dp value in the for loop, right? So say currently we are at dp of 14. Currently we are at this iteration where we are calculating where I is 14, right? We'll add dp of 14 to the running sum so that dp of 15 can use it. Yeah, that's the idea. And if so, this is at the front end of the running sum. If I is less than k, we can freely add dp of I to the running sum. If not, we cannot add it. But here's the elegance. What we can do is actually add it to the result, right? Because the result will only contain dp values which start from k and go until n, and this for loop ends at n. And if we if I is if we are at the threshold or at any value greater than the threshold, we can't add it to the running sum, but we can add it to the result. So let's just do that. right? Cool. And now we'll handle the tail end of the running sum. Cool. And this is where we'll also consider the um, first edge case, the zero end edge case, right? This one. Uh, oh, okay, I haven't added an example there, but I hope you remember. Um, if I is if I minus max points is greater than equal to 0, right? We can only add dp values which are at 0 or greater than 0. We can't have dp values of i's which are less than 0. That makes no sense. Just handling that. This is the first edge case that I told you about, the zero end edge case. If everything is okay at that end, we'll just remove the dp value from that end, right? And you have to remove the dp value at the maximum end at the back, so that we can get by subtracting by max points. That's the maximum back you can go, right? And that's it, right? Let's just return the result. Cool. Let me check if I missed anything. Okay, I've missed an edge case. So this k equal to 0 edge case we understand. Now, what is one other case where the probability of Alice having n of fewer points is also maximum? What happens if the max score that we can get from this game? What happens if n is greater than the max score we can get from this game? The probability that we'll always have n of fewer points is 100%, right? Because the maximum score we can, if n is greater than the maximum score we can get from this game, we'll always have 100% probability for this, right? So let's just handle that. Cool. I think let's run this code. Accepted. Cool, that works. I hope that explanation was clear. I'm recording after a long time, so I apologize because I was a little rusty today. But happy lead coding, guys. Stay safe. Have a good day or a good evening wherever you are. Bye.